Welcome back. We talked in detail about the van der Waals interaction or the free energy of interaction due to van der Waals forces between two surfaces or two blocks. And we are now convinced that indeed as compared to two fundamental particles where the interaction scales as 1 by r to the power 6, between two surfaces the interaction is 1 by d square. In addition to that, we have now realized that there can be excess free energy in a thin film. We have derived an expression for that, and we have also found out another criteria for understanding whether a film is stable or not, and that is based on either the effective interface potential or the disjoining pressure, whichever is, it is essentially the same thing. So, this is a handwritten slide which I used to sort of trigger the discussion on spontaneous instability, and if you look into that lecture, what you will see that only this part I have added based on what we discussed in the previous 3 lectures, only this part. So, what is it? While I discussed about the stability and instability at this level, right, I talked about or tried to explain it only in terms of spreading coefficient. What I implied or emphasized if the spreading coefficient is positive, that means that by coating the film you have in fact reduced the total surface energy. Therefore, the film is unconditionally stable. What on the other hand, if the spreading coefficient was negative, then what it implies that coating the film, or rather I would replace this word liquid with film, has led to in fact the liquid partially wets, or by way of coating the film you have in fact increased, or we have increased the total energy, and therefore, thermodynamically this film is not stable. But there was a limitation, or there is in fact a limitation of this spreading coefficient based approach, and that is the expression of spreading coefficient does not consider the film thickness. So, based on spreading coefficient you will get that if you try to have a 100 micron thick layer of water on a surface of Teflon, 100 layer, which we have no harm in marking that as a film, thick layer of water on a Teflon surface. Why I am giving this example? Because water, many of you know by now, gamma H2O is 72.8 millijoule per meter square. Teflon is of the order of 12 millijoule per meter square. Plug in the values, even if you assume gamma interfacial tension is of the order of 5 or something like that, you are going to have a significantly negative value of spreading coefficient. So, based on spreading coefficient, what you will get that this thick layer of Teflon, a thick layer of water on Teflon is going to be unstable, right. That is what your spreading coefficient alone will tell you. But reality is this film will remain there, nothing is going to happen to this film, because the film is too thick, and those surface fluctuations will never get adequate help from the interfacial van der Waals interaction to grow. They will always be flattened out because of Laplace pressure. However, if you now look into this effective Hammarkar effective interface potential, what we have got from the consideration of the excess free energy, how the excess free energy. So, let me also write down its expression as delta delta H of delta G LW excess. Okay. So, what does it give? It actually gives you an idea how the free energy, the excess free energy of a thin film changes with change in the film thickness. So, what it means that because of this fluctuation, there is change in the local thickness of the film, and as a consequence or as a result of that, the excess free energy also changes. Now, we understand, or what we very nicely discussed towards the end of the previous class, is that for the film to become unstable, it is necessary that the oscillation grows and simultaneously the free energy also reduces. Otherwise, the process will not evolve, because it is a spontaneous instability. And that gives you a necessary condition for film instability or the film to become unstable is effective Hamarkar, effective interface potential, effective interface potential phi Lw must be positive. What is the advantage? Advantage is, and that becomes positive only when your Hamarkar constant is also positive, the effective Hamarkar constant is also positive, because of the fact that this particular term 6 pi h cube is always going to be positive, and therefore, effective interface potential will be positive only when Hamarkar constant is positive. That is fine. But what is the advantage of looking into effective interface potential as compared to, let us say, spreading coefficient? The advantage is its expression contains h, and therefore, if you look into this type of a system, right, you might have A to be positive, but since the expression contains h, it will not indicate a positive value, but it will indicate phi Lw to be equal to 0, and therefore, you know that you have failed to satisfy the necessary condition of instability, right. So, I would put it, and as we are sort of strengthening our concepts based on slowly from spreading coefficient to effective Hamarkar constant to now the effective interface potential or the conjoining and disjoining pressure, this is in fact probably the best benchmark to identify or examine whether a film is thick or thin. Of course, one of the necessary condition is AE is positive for the film to become unstable. We have had enough discussion on that. I am not going to repeat it, but then you can have situations where AE is positive, but the film eventually remains stable. It is simply because of the fact that H is too high, too large, and therefore, this term, because the denominator becomes so large, tends to 0. And then you know that, well, you have a thermodynamically unstable film, but it is actually stable, it is stabilized by gravity. There is too much amount of thickness, there is too much amount of material, and your van der Waals forces are too weak to grow by dislodging so much amount of material. Okay. So, now coming back to the issues related to Dewetting, what we had discussed quite a few points. In fact, we now know that the spontaneous instability observed in a liquid film is in fact a long wave instability. We also know that before the film ruptures, there is in fact a competition between disjoining pressure, which tries to destabilize the film, and Laplace pressure, surface tension driven Laplace pressure, which tries to stabilize the film. So, essentially, as long as the film has not ruptured, surface tension has a very nice role trying to maintain the film integrity. However, the moment the film has ruptured, in fact, the whole growth is favored by surface tension. So, there is in fact a role reversal of surface tension before and after the rupture of the film. We also know that hole formation is not that simple as we have talked about, or particularly the retraction and the Dewetting part, because there is a mismatch in the rates at which the material is dislodged from the surface and it is distributed to the intact parts of the film, and that often leads to the formation of a rim around a growing hole. And in fact, it turns out this rim profile sort of gives a lot of idea about the viscoelasticity of the film. So, if you have long chain polymer which is due to entanglement effects more viscoelastic, in fact, the rim profile becomes very skewed. I mean, it becomes very sharp in one of the sides, inside and outside it is pretty slanted. I will skip all the details for the time being. Anyway, so Let us have a quick relook at these two videos. So, what are the things you know now? You know that the film is rupturing, therefore, you know the spreading coefficient is negative, you know the effective Hamarker constant is positive, you know the effective interface potential is positive, etc., etc. You see that it and this is the late stage thing where we also talk that in fact the adjacent rims join up. These rims lead to a cellular structure comprising of very tall high aspect ratio threads, which eventually break down due to what is known as Rayleigh instability. You are more than welcome to check in the net about a little bit more detail about Rayleigh instability. I will not get the time to cover it in the course, but there is something very, very interesting. So, it is essentially if you have a long liquid thread like this, it tends to become oscillating and undulating because of effects of surface tension, and it eventually disintegrates into droplets. In fact, if you can do a very simple experiment with a regular tap. If you try to turn off the regular tap, or if you sort of make the flow very, very thin, and it sort of I mean just ahead of closing the tap, you see that, so this is let us say the tap, the flow is much reduced. So, you see the meniscus has become like this, and then you have you observe that water is falling in drops. So, you have a feeling, well, I have almost closed the tap nearly fully. So, the supply is intermittent and therefore, we are seeing drops. That is not the case. In fact, the supply is continuous, but it is a very low supply, and then ideally it should form a long cylinder of very tiny thread or cylinder of water, which in fact disintegrates due to Rayleigh instability into these droplets. Okay, you can try it out yourself. So, as I mentioned, there are certain issues related to this dewetting, like this rim profile is important. There are a whole lot of other stuff which I do not want to really complicate things and make things difficult for you, but some of the observations are that one many times observes that films which are thermodynamically stable. So, let us say where the spreading coefficient is positive, right, or the effective interface potential is negative based on the value of Hamarker constant, these type of films are also showing dewetting and following almost a similar mechanism. So, people started to argue that there must be some additional fields that are responsible. It is not only the van der Waals force driven growth, and people have come up with lots of arguments, like one often argues that heterogeneous nucleation is responsible, but nucleation typically requires surface inhomogeneity, and why across almost every sample the surface inhomogeneity is uniform is a matter of debate. So, people also came up with more creative thoughts, for example, like there is accumulation of residual stresses during spin coating, which slowly get reduced, and as a film is reheated beyond its glass transition temperature, depending on the magnitude of the residual stresses stored within the film, it can rupture. So, there are some pioneering works in this particular area. I will as I mentioned, these are too much of research level areas where contributions are coming in last 5-6 years or maybe last 2-3 years. So, I will not go into too much amount of details, and I will focus on something that is a bit more general. So, there can be other issues like so this is that cellular structure I was talking about. So, you see if you have these cellular structures, the drops are not completely isotropic like what you see here. Here it is like a completely random collection of droplets, but here you see that the drops sort of are arranged according to the sort of contours of the cellular pattern, but here you see that the drops are completely random. Well, it turns out that in this latter case, while retracting, the rims themselves sort of started to show some sort of an undulation and was leaving behind secondary droplets as the hole was growing. So, there are lots of issues like this, and which I really do not want to get into in this course. Maybe if I offer a second level advanced course on dewetting, I will talk about all these issues. This is again something I will skip. I will now talk about a very fascinating situation, that is if it is a liquid-liquid bilayer, and what happens if a liquid forms, or if a liquid partially wets a liquid. So, if a liquid partially wets a solid, you know this is the configuration, Young's configuration, this is what is called. You are too well conversant with it by now. But if it is a liquid, then what happens if the bottom layer is also a liquid, and you can do that, you can put some, let us say, water on some glycerine or some honey or something like that. The top layer liquid, in fact, the vertical component, I just briefly mentioned what happens to the vertical component. In fact, the vertical component does not manifest in any way on a rigid surface, because the surface is too stiff to sort of exhibit any effect of this vertical component of surface tension. But that is not the case when you have a liquid, because it is a deformable liquid-liquid interface. Therefore, you observe some deformation on the bottom layer also, and this is typically the equilibrium configuration of a drop of liquid 2 on an intact layer of liquid 1, and it is sort of given by a I mean, let us not, I will not talk about it, okay, leave it. But this configuration is called the Neumann configuration. An important reason why I talked about this particular example is an important class of problem is instability in a bilayer. In fact, where both the layers are adequately thin and both can duet. So, you see, instead of a single layer film, now there are 3 interfaces and 2 deformable interfaces, and there is absolutely no reason to believe that all the 3 interfaces will become unstable, or both the layers will become unstable together. In fact, it turns out that one of the layers becomes unstable first, and that sort of dictates the initial evolution pathway. So, easiest way to think about it, it is very nicely written here, shown here. Suppose you have a bilayer comprising of 2 films. On the left hand frame, what you see is a situation where you can read a lot of literature on bilayer duetting by wonderful theoretical work by Professor Dipankar Bandyopadhyay at IIT Guwahati, along with Professor Ashutosh Sharma, who have contributed immensely into this field ever since 2005. Initially, they contributed a lot of experimental theoretical papers, and then some of them have been experimentally validated, because doing experiments with a bilayer is extremely difficult, because tracking an interface with an AFM, you now understand AFM. So, you now understand that if you have a bilayer, the AFM will only give you an information about the top layer. It will not give you an information about the submerged interface, and therefore, tracking a bilayer duetting is an extremely difficult thing. However, there have been experiments on bilayer duetting, and those experiments are going on from mid 90s. But it is this particular group from Professor Sharma's group that the theory of duetting bilayer has almost emerged. Okay. So, what can happen in a quick way we can let us investigate? It is that in this particular case, the strength of interaction between the film-film interface and the film substrate interface is stronger than the interaction between film-air interface, the free surface of the liquid 2 and the film-film interface, and as a result of which this layer, bottom layer, becomes unstable first, and as a consequence of that, the top layer simply follows that. This mode of instability is known as the bending mode of instability. So, after the bottom layer has ruptured, so bending mode, you now understand what I have drawn. The bottom layer has ruptured. So, this let us mark this as 1, this as 2. So, what happens over these areas, now the film 2 comes in direct contact with the substrate, and again now one needs to look into the sign of the effective Hamarkar constant between 2 and the substrate. If depending on whether this is positive or negative, if it is positive, then there is a possibility that this particular layer will also rupture, and as a result you are likely to get structures like this. Or there is a possibility that the interaction here is repulsive between this surface of 2 and the substrate, and therefore, this is the permanent, or this is the final morphology. Either of which from the standpoint of fabrication is very exciting, because see here by simply duetting a bilayer, one has lead to some core shell droplets. And here one has lead to some submerged droplets. Right? You have learnt adequate amount of nanofabrication in terms of soft lithography, photolithography. Fabrication of both are very difficult. So, therefore, instability is not only scientifically very exciting and interesting to study, but it has the potential to fabricate some novel structures which are difficult to realize by classical or conventional top down lithography techniques. What is the only problem? The only problem is something you have already seen, and that is the structures are random. Therefore, what we will learn in our next class is how to align these structures. But before that, let us look into the other possibility that can happen with a bilayer, and the other possibility is the interaction between this surface and this interface is stronger than this one, and in that case what will happen, the evolution will be like this. This is what is known as the squeezing mode. It in fact is a bit interesting, because here both the interfaces are deformable, and as a consequence of that you see that the top free surface sort of comes down, but since there is an attractive interaction, this liquid interface also goes up, which is not the case here, because here this surface, the one of the surface, that is the film, the liquid solid interface that is participating in the initial instability is rigid, and therefore it cannot deform. However, here since the initial interaction is stronger between these two interfaces, it deforms like this, and resulting in initial structures which look like this. Did you see them somewhere? Yeah, of course. You actually have drops of 2 resting on a layer of 1 following the Neumann configuration, right. So, now of course, the question comes whether a film of 1 is stable on the substrate or not. You can understand it very easily, and if the Hamarkar constant, the effective Hamarkar constant is negative, which means that the 1 is stable on this surface, then of course, this is the final morphology. If not, then of course, there are other issues. In fact, there, even if this is stable, there can be other considerations. So, let me just spend a few minutes, couple of minutes on that. So, after the initial rupture and dewetting has taken place, this is the configuration. And maybe one of the assignments we can have is to find out the conditions, Hamarkar constants under which this thing happens. So, now there can be three possibilities. Simplest one, this film is stable everywhere. So, you see this film 1 in fact has two different types of areas, right. One area is you only have a layer of this under air. The other area is where it is submerged between drops of 2. So, if the film 1 is stable at both the locations, then this is the final morphology. But there can be other possibilities that these areas it is unstable and these areas it is stable. So, then it might lead to some eventual structures like this, sorry, these lines will not come, some sort of structures like this, or if there is a possibility that these areas it is unstable and these areas it is stable, then it can lead to some coexisting structures. In fact, liquid can squeeze out from here and 2 might in fact eventually come in contact with 1. So, all these possibilities are there in a bilayer, and it depends on the strength of the interaction forces across the different interfaces at different times. Film thickness of course is a critical thing, because if one of the layers is thinner than the other one, of course the possibility of that particular combination, that particular film rupturing ahead of the other one is more. But there are issues like wettability, relative spreading coefficients, Hamarkar constants, and also the viscosity, because the film might be unstable, but if the viscosity is too high, the molecular weight is too high, the dynamics might be too slow. Anyway, so bilayer dewetting again is a topic in itself, and I just gave you a glimpse of some of the exciting possibilities that are there, how the complexity sort of increases many folds when there are two deformable interfaces which involve their coupled deformation. But one thing we have realized, that bilayer dewetting or dewetting as a whole has the potential to offer a novel nanofabrication technique, because all you do is you start off with a thin film and you eventually result or lead to some structures which you otherwise do with lot of difficulty. But the problem is, the limitation is, these structures, the utility of these structures are severely limited by their randomness. And next, therefore, what we are going to talk is the possibility of aligning these dewetting structures typically on a pattern surface, which can be a topographically patterned substrate fabricated by any one of the soft lithography techniques we talked about, or maybe even chemically patterned substrate. Okay. So, that is the next thing that is going to come up next. Thank you very much.